All right. Welcome everyone back to AE 311. Today we're going to talk about solid angles. And this is one of the most challenging concepts that I'll be addressing in 311 this semester. So strap in for a challenge today. So solid angles are important because light propagates radially in straight lines, as you know. So it's best characterized using a spherical coordinate system, which is why we need to define things using solid angles, including the photometric reports that we use to characterize the distribution of light coming from luminaires. So if you have one sitting around near you, I do recommend grabbing some kind of a ball, especially one you can write on, if that's even possible, because that's going to help you visualize some of these coordinate systems as we move through the content today. So let's start with some definitions. We have our solid angle, which is the field of view from a particular viewpoint. The symbol we use for that is omega, and the unit is going to be in steradians. This is like degrees, it's a dimensionless unit, and it's going to define everything that is inside a cone emanating from an origin. So let's take a look at some of our options here. Viewpoint matters. Viewpoint matters a lot when we're talking about solid angles. We can use solid angles to define the size of objects in our field of view. We can also use it to define the field of view of a sensor. But really what we're getting at today is defining it, or using it to define the intensity of light in a particular direction. Before we get to that though, let me start with something a little more entertaining. So let's take a look at that sun, moon, earth system that I used in the title slide. This is a classic example of the way that solid angles work, and also really highlights how important it is to diagram your problems so that you get these angles and viewpoints correct, because these type of problems get complex in a hurry. So let me give you a useful equation here. So the solid angle omega of an object at a distance is defined simply by the circular area over the distance squared. So that's a fairly straightforward approach. Here's some values for both the sun and the moon. So if you could all take a moment and let's calculate the solid angle of the sun and the moon and see how well this works out for solar eclipses. This formula isn't particularly relevant to lighting design per se, but I do like to include it, if only because I find it weird that we never calculate actual objects out in space. So when we take a look at the solid angle that each of the sun and the moon subtend to, what we see here is the sun is only about 5% larger than the moon in terms of the visual angle, right? And this is why viewpoint matters so much, because this doesn't cover me until it gets closer to the camera, right? So this is exactly why we get such nice solar eclipses, is just pure coincidence that the sun and the moon system tends to have the very similar visual angle from our viewpoint on the surface of the earth. And just a little bit more candy before we get into the meat of this lecture. This is the path of totality right here for the solar eclipse coming up in just 3 years on April 8th, 2024 at 3:15 p.m. There will be a solar eclipse just to the north of us. For those of you that have not seen totality in a solar eclipse, trust me, it's worth the drive. Okay, so let's dig into spherical coordinates a little bit more here. So here's a great example, bringing us back to Earth. these cones here show the coverage of exactly 1 steradian. And so the way that works is we have a cone that's projected onto the surface of a sphere revolved around a central apex angle. And the definition of 1 steradian here is any area on the sphere which is equal in area to the sphere of its radius when observed from the center is 1 steradian. But let's take a look at the way that this is built here. So first off, we have the central angle of the cone, right? So we have a central angle theta, or actually 2 theta, and this is important. Don't forget that when we're going to apply this to our equation coming up, this central angle is actually 2 theta. And the central angle is the angle at the apex right here in the center of the sphere. This is important because this is where the viewpoint emanates from. So the apex of the sphere is where you're going to place your sensor or your luminaire, or that's maybe where your eye is, depending on what type of solid angle you're interested in calculating. So some rules of thumb here that are helpful to know. There are 4 pi steradians in the whole sphere, in any sphere, right? So this sphere could be 6 inches in radius. It could be 6 feet in radius. There are exactly 4 pi steradians in any sphere. In a hemisphere, for example, the sensor, the cosine sensor on a illuminance meter, in a hemisphere, you have just 2 pi steradians. So those are some useful rules of thumb and some shortcuts depending on what type of problem you're working on. Now, let's put this into an equation to make this a little more useful. So here we have omega, or the solid angle, is equal to 2 pi times 1 minus cos theta, theta being half of that central angle right up here. Yeah? So if we have the central angle of our cone, that's 2 theta with respect to this equation here. And this is going to define the solid angle of a cone, which is the simplest solid angle. We're going to get a little more complex here in a bit, but for now, this is where we want to start. Now, this equation works both ways. We can solve for theta to get the visual angle of a disk, or we can solve for omega to get the solid angle. And when we're talking about the visual angle of something, we're really talking about that central angle at the apex of this sphere. Let's talk about this in terms of our fovea. So, as we recall from the vision and perception lecture, the fovea is the center part of our vision, the high fidelity piece of our vision, where we get the most information. That's where we read and see in fine color detail. So the question is, what is the solid angle of our fovea? The fovea is typically referred to as the central 2 degrees of your vision. So that does, this does evaluate to 9.6 times 10 to the negative 4th steradians. And the key thing there is to use the central angle of 2 degrees, and you need to half that before you plug it into the cosine function in this equation. Okay, moving on, let's talk about goniophotmetry. So if you remember that monstrous device I was discussing on Monday, goniophotmetry is how we get Candela tables. And that's a measure of the intensity of a light source at each relevant angle around that light source. So let's start by defining our coordinate system so that we can take a look at the way these Candela tables work. So step 1, we were going to place the luminaire at the apex of our sphere. I'm going to leave the sphere off for just a moment here. Step 2, we're going to define zero vertical as straight down from the emitting face of the luminaire. So that's straight down is zero vertical for almost all types of luminaires. The exception to this would be spotlights, which is going to be straight out from the face of the spotlight. But of course, that could still be down and often still is. So for typical architectural luminaires, they're going to be ceiling mounted. They do have an orientation, and so it's very straightforward to define zero vertical as straight down towards the floor. Our next step is defining 0 degrees horizontal, and we're going to define that along the longest axis of the luminaire. And in this case, it doesn't actually matter whether we defined it going that way or this way. And we're going to get to why that is in just a moment here. But first, we need to toss in the globe. There it is. Okay, so here is our spherical coordinate system, and those are the origins of the spherical coordinate system. Keeping in mind that 0 horizontal, as opposed to, say, lat and long coordinates, 0 horizontal is going to be placed along the equator, and 0 vertical is the South Pole, as you might expect. So what we're doing with each of these rectangular elements here, so each of these rectangular elements of the sphere define one patch through which we're quantifying the intensity. So each of these patches will have their own associated intensity in our Candela table. We can also use type B goniophotometry. Now, this again is for things like outdoor floods, like sports lighting, spotlights, and you can see why you would redefine this coordinate system in this manner, because we're more interested in the way it works around that axis. That's not as common for architectural luminaires, so we're not going to talk about type B goniophotometry. I just want to make you aware that it exists. Type A is also a thing. It's almost exclusively used in the automotive industry. We don't talk about type A in this course anyways. Okay, back to type C goniophotometry. Let's associate this with a Candela table. So here we have a Candela table, and what you see is a set of angles along the side and at the top of this table. And then inside the table is a set of values. These are all intensity in Candela at these angles. So the example luminaire I'm using, and I'm going to use this throughout this lecture today, is this suspended linear pendant luminaire. This is a very common type of architectural luminaire. And if you'd like to dig into this luminaire in particular, the link in the bottom right corner will take you to the product page, so you can look up all this information yourself. Okay, so the first thing we're going to do is define our vertical angle range. And typically speaking, we're much more interested in vertical angles than horizontal ones for most architectural luminaires. So something that's very important to point out, recall that 0 vertical is down here at the bottom, the South Pole, if you will. And so as we increase from 0, we're actually going to go up along and eventually get to the North Pole on our sphere. And that's our range of vertical angles. They only go from 0 to 180 because we're going to account for the other side of the sphere with our horizontal sweep. Now, this is where it gets fun, is the vertical angles in the table start at 0 and go down, right? So this is actually, this value up at the top of the table is straight down, and the value at the bottom of the table is straight up. So keep in mind that when you're incrementing vertical angles down the table, you're actually moving up on this sphere and going higher and higher and higher. Okay, let's add the other piece of the puzzle in. So we have our horizontal angles, and our horizontal angles are going to be an equatorial sweep around the sphere, right? And fortunately, those mostly increment as expected, as you can see. So as we increase our angle, we're just going to keep going around the sphere. Now, here's a fun question. In this Candela table, we only have horizontal angles from 0 to 180. But I just told you they go from 0 to 360 to do a full equatorial sweep. So what's going on with this Candela table, and why is this Candela table not providing us values for the entire other half of the globe? The answer is symmetries. So this is a shortcut to the way we construct these tables, and it's also why it doesn't matter if we define 0 horizontal on this particular luminaire going that way or coming out into this direction. So either one is going to be equivalent, because if you flip that luminaire 180 degrees, it's symmetric and there's no change. So let's take a look at those symmetries here real quick. So we have 4 basic types of luminaire symmetry, and these are going to change the way our Candela tables look depending on what type of symmetry we're talking about. When we have an axially symmetric luminaire, it means that it doesn't matter which slice we are taking around the globe. So like a spotlight, whether I'm here, 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 or here, it's all going to be identical, right? So this is an axially symmetric luminaire that has all of these slices the same. And so a great example of that is an A lamp. Par lamps are also axially symmetric. There's spotlights, of course, are also axially symmetric. So in the Candela table, we're only going to have a single value for horizontal angles, because no matter where we are on this globe, all of these slices are identical. So we only need a single column, because that column is good for this set of angles as well as this set and all the others. Moving on, we have quadrilateral symmetry. So this is where you can rotate it 90 degrees or 180 or 270, and you're going to have symmetries in all 4 quadrants. So you only need to define a single sweep from 0 to 90, because each other sweep of 90 degrees will be identical to the first. The most common example of that is troffers, or 2x4 troffers especially, that fit into the standard gypsum ceiling tiles in most common ceilings. There's a variety of other quadrilaterally symmetric luminaires. We're also usually talking about pendants, linears, strips, are all going to be quadrilaterally symmetric as well. Also have bilateral symmetry. And so here's an interesting thing about that last table. It went from 0 to 180. If you actually look at the values, though, it's actually quadrilaterally symmetric. So they're providing you more values than you really need, because bilateral symmetry is going to be like this grazer here. So this luminaire that I'm showing is actually a chalkboard grazer. So something that will go over the top of a chalkboard and push light down onto that surface. And so it's no longer symmetric. It's no longer symmetric from front to back, but it is still symmetric from left to right. So we can slice it straight through the center like that, and the left side and the right side will be the same. And so in that case, we have bilateral symmetry, which means that we only need to define the Candela table from 0 to 180. And our last option is asymmetric luminaires. And so these luminaires are different in every angle. There's no symmetry at all. So you're going to need to use a full 360-degree equatorial sweep to fully characterize the distribution of light coming from a luminaire that looks like that one. Okay, so let's bring this back to our Candela table. And again, we need to consider where the location of these angles are on the globe. So we start with 0 degrees vertical, right? And as we move up in our vertical angles, right? 45, the equator is 90 to 135 to 180 at the North Pole. And so those are our vertical angles. And each vertical angle is going to bound. So each pair of vertical angles is going to bound an unequal size slice on the surface of this sphere. So this is an important part of vertical angles in that the slices they bound are not all equal. That's why we don't define symmetries across the vertical angles. We define them around the horizontal ones. Because as you can see on this ball here, the horizontal angles, so each of these panels represents a 30-degree shift. So we can go from 0 to 30 to 60 to 90, and each of those panels is identical in their size, no matter where you're at on the globe. So that's why we have symmetries across horizontal angles and are able to truncate these Candela tables across horizontal angles, but not across vertical angles. Now, let's take a closer look at the way this table is set up. So when we look at a particular entry and locate each of these values on the surface of a sphere, right? So if we're going to start with 0, 0, what we need to do is go to the bottom of our sphere, right? And so 0, 0 is the patch, and it's actually going to be a circular patch in this case, centered on the South Pole, right? So that's our 0, 0 patch, and it's going to be bounded on the bottom or on the top. In this case, see, we go from 0 to 5. So the edge of this patch actually lies at 2.5 degrees vertical. So we come just 2.5 degrees up. And then the horizontal patch goes from 0 to the next one is 22.5. So the boundaries of that will be at 11.25 and negative 11.25. So that is our patch right here. It's more circular than most of the other patches. As we come up, we're going to be looking at rectangular patches, right? So we can pick another place on the sphere. So let's go to 90 and 90. So in this case, it's 0, and we'll get to why that is in a moment. It actually has a lot to do with the way that luminaire is built. So if we're going to 90, we're going to start at the South Pole and then move our way up to the equator. So there's 90 vertical, right? And then to get to 90 horizontal, we need to rotate through 1, 2, 3 of these patches as 30, 60, 90. And so here is the center of the coordinate 90, 90 on this Candela table. Does that make sense how we move around the sphere? So we move up as we increase our vertical angle, and we move around as we increase our horizontal angles. And each of these patches is a rectangle projected onto the surface of a sphere. So we define the edges of those by going halfway between the box we're interested in and the next box up and the next box down. Yeah. So let's take a look at that in an equation form and define the solid angle of a particular rectangular patch. And as you can see on this sphere, the size of these rectangular patches changes as you move through different vertical angles. So as you go around in horizontal angles, the patches are all the same. But if I move up from the equator to say 135 degrees vertical, this is actually going to give me a different size rectangular patch, a smaller one than the ones at the equator. So we need an equation to calculate the size of those projected rectangles on the sphere in terms of solid angle. So here's that equation. The solid angle for a rectangular projection. So let's take a look at this and break this down just a little bit, and then we'll apply it. So first off, we have V2 right here. So this is the second vertical angle, or the higher up vertical angle. So if we're talking again about the vertical angle at 90, 90, V2 is going to be halfway between 90 and 95. So in that case, V2 is 92.5, and V1 is going to be halfway between 90 and 85. So V1 will be 87.5 in this case. Similarly, with our horizontal angles, we take the larger horizontal angle minus the smaller one. So our horizontal angle 2 in this case is going to be halfway between 90 and 112.5. And horizontal angle 1 will be halfway between 90 and 67.5. So that's how we define the boundaries of these rectangular projections in a way that allows us to calculate the solid angle of that rectangle on the surface of the sphere. So let's do another calculation question here real quick. This time, what I'm asking you to do is calculate the solid angle for the zone containing the peak intensity in this table. So this equation for peak intensity evaluates to 0.031 steradians. And let's break down how that works. So first off, there is our location for peak intensity over there in the red box. So this is at a location of 115 degrees vertical and 90 degrees horizontal. The next step in this process is defining the vertical angles 1 and 2. So going just above 115 and halfway to 120, we get to 117.5. And on the bottom side, it's 112.5. So that's theta V2 and V1. And then our horizontal angles are going to be defined similarly. So we need to go halfway between 90 and 112.5 to get theta horizontal 2. So that's 101.25 degrees. And then theta horizontal 1 is halfway between 90 and 67.5. So those are the values we need to plug into the equation, and that's going to give us the solid angle of the location of peak intensity. So if we think about this on our sphere, the way this, where this is located, so again, our long axis for this luminaire is at 0 horizontal. So we're actually going to rotate around to around 90 degrees. So the peak intensity is coming off the side of this luminaire. Now, when we're looking at the vertical angles, what we're doing is we're moving all the way up to 115. So peak intensity is actually, we're moving all the way up, and we keep going past the equator because that's just 90. And so it's actually above horizontal. So peak intensity for this luminaire is actually emitted up, not down to the work plane, but up into the ceiling. Talk quickly about the zonal lumen summary, which is another important aspect of our photometric report. Now, what this does is quickly gives you the gross vertical distributions of the luminaire. Oh, yeah. Uh, David, you are absolutely correct. You do have to use radians in that equation. That's where the breakdown is. So the resulting value is steradians. So the input values need to be radians. So you do need to convert that, or at least evaluate those functions to be radians in the output. So yeah, actually, thank you, David, for pointing that out. I appreciate that. That is an important detail in how to get the correct values out of that equation. Okay, let me start over um, on this. And yeah, Zach, oh my God, While My Guitar Gently Weeps on Across the Universe, absolutely incredible. Everything that Sadie and JoJo did in that movie was incredible. Okay, zonal lumen summary. So what the zonal lumen summary is telling us is the gross distribution of light in each of the vertical zones. So you can see at the top there, we start with just 0 to 30. So that's basically our direct down component, right? So if we're below our luminaire, it's the light that's emitted almost directly because it's going to be this part right here on the bottom. So that's the light emitted almost directly onto your work plane, right? Now, there's a variety of different ways we can break this down, but I just want to highlight some of the important pieces. The next important piece, I think, here is actually the 60 to 90 zone. And so the 60 to 90 zone, if we're looking at our sphere here, so we're going up to 90. So it's this zone right here, right? So that's our 60 to 90 zone. Why the 60 to 90 zone is relevant? This is our glare zone. That's our glare zone. So if your luminaire has a high output right along vertical, those are the kind of sight lines when you're looking across the room where you can directly view the luminaire. And that's not great if it's putting out a lot of light right below horizontal. So right below 90 in that 60 to 90 zone is what we call our glare zone in the zonal lumen summary. And so you can see this luminaire actually intentionally cuts that off here. And there's only 6% of the total lumens are emitted within that glare zone. So that's definitely a plus for this luminaire. And that's part of why you see this band right around the vertical here that goes to 0. It's eliminating glare. And then the final zone worth considering is actually this bottom one right here. So this is 90 to 180. And so in other words, this is everything above the equator, if you will. So it's all of the lumens emitted toward the ceiling. So as opposed to this section here, which is the direct onto our work plane, when we're talking about everything above the vertical, we're talking about ceiling illumination. And so this is the important zone for indirect luminaires that are emitting a lot of light up onto the ceiling. This helps give us that soft shadowless ambient fill light that's so useful for visual acuity. And it also helps enhance spaciousness by highlighting the ceiling and expanding sightlines upwards. So those are some of our zones of interest, and the zonal lumen summary can give you a really quick look at the performance of the luminaire in those particular zones, and that'll give you an idea of how to apply that luminaire effectively. Polar plots. Okay, so this is actually where all of this information becomes useful. So this Candela table, even though I just made you figure out how to utilize this, Primarily, this is something for your computer to utilize. You're very rarely going to actually try to look at this thing and make any sense of it. This is just a pile of numbers, and it's not that intuitive to figure out what the distribution of the luminaire looks like from a table like this one. So instead, we're going to look at a polar candela distribution or a polar candela plot. And this is going to give us a more easy to understand visual representation of the distribution of this luminaire. However, it's easy to misinterpret this too, which is why we're going to take a moment to break this down. Bring back my trusty beach ball. So what's happening here, each of those lines, the red line and the blue line, are representing different horizontal slices. So it's representing all vertical angles, as you can see here, from 0 all the way up to 180. So it's all of our vertical angles for this luminaire. However, each line is only a single horizontal slice. And you can see in the key right here that the blue line represents the 0-degree horizontal slice and the red line represents the 90-degree horizontal slice. So essentially, we're taking slices perpendicular to each other, so we can get a quick look at the way that light is distributed from this luminaire along the long axis and along the short axis. And so the blue line is our long axis distribution at 0-degree horizontal, and the red line is going across the luminaire's short axis at 90 degrees horizontal. There is our slice on the Candela table. So we have our Candela table here. And so here's our 0 degrees horizontal slice, which is represented by the blue line over here on the polar Candela distribution plot. And then we can add the red line. So you can see the red line over here is going to be found on this table along the 90-degree horizontal column. So that's where you can look up these values directly. And also with this plot, importantly, remember, we're not representing horizontal angles here. So what the radius is representing, or the distance from the origin right here, what the radius of this plot is representing is actually intensity. So when we're further away, like right here at the end of the bat wing, you can see that maximum intensity is right there. So the further we are from the origin, the more intense it is. So you can see this light is primarily pushing light straight down and then up and out above the horizontal axis, above the equatorial axis, if you will. Okay, so this is a bit difficult to understand this way. So let's take this forward and superimpose these distributions on the luminaire itself. So there we have it. So you can see along the short axis, what this luminaire is doing is pushing light straight down and straight out. This is what you call a classic bat wing distribution. And what this is trying to do is push light out to cover the ceiling, because the assumption for a pendant luminaire like this is that you're much closer to the ceiling than you are to the work plane. So you need to push light down to the work plane, and you've got room for light to mix, but you might only be a foot from your ceiling or even less. So you want to push this out as wide as you can to provide even coverage on the ceiling. Now, when we look at this side over here, that's not really what we need. What we need is just an even distribution, pushing it up and down. And so along the long axis, that bat wing disappears because we're not pushing it out off the ends of this luminaire. We're pushing it out from the sides of the luminaire. So I've got one more visualization to help you understand the way these polar candela plots are representing the distribution of light. And we can look at this as a projection onto a wall. So here we have this luminaire actually in a real space. So this is a real photograph of this luminaire installed in a real space. You can see it's a pendant luminaire hanging down, and you can see that batwing distribution up above it, and the straight down distribution pushing light down towards the work plane below it. So let me increase the contrast on this image here, and that helps you see that batwing even more clearly, right? So you can see how it spreads above and pushes down. And so this is how we can utilize polar candela plots to understand what kind of output we're getting from our luminaires. And when you're looking up luminaires online and looking at their cut sheets, as you will for your design project this semester, the polar candela plot is the fastest way to educate yourself on how that luminaire is distributing its light. So let's take a look at a couple more examples of this. So here we have some can downlights that are pushing light onto a wall. Here is the polar candela plot for these luminaires right here. So you can see that it's pushing light straight down in one direction with a fairly narrow distribution. So I have a couple questions for you. And that is, what is the symmetry of this luminaire? So our options are axial, quadrilateral, bilateral, or asymmetric. And what type of light is this luminaire typically? Obviously, you can change this, and the way you apply the luminaire matters. But typically, what type of light does this kind of luminaire provide? This luminaire is, in fact, actually symmetric. And part of the reason you know this is actually the candela plot itself. Notice it doesn't provide a second horizontal angle, even though down here in the key, it actually has a option for the 90-degree horizontal angle, but it's simply not shown. And that's because the 90-degree and the 0-degree are identical. And in fact, all horizontal angles for this luminaire are identical. This is an actually symmetric luminaire. And the reason you would use this, so this is a can downlight. The reason you would use this is to highlight a particular visual task, or in this case right here, accent a wall. So definitely accent lighting is the way to go given this photo. Okay, here's another luminaire to consider. So this one is a wall sconce, and this time we have a bit more complex of a distribution here. So take a look at that distribution carefully. And the question again is, what type of symmetry does this luminaire exhibit? And also, what type of light is it typically providing? How are we typically going to use it in architectural lighting design? This luminaire is, in fact, bilaterally symmetric because it's pushing light towards the wall. And typically, we're going to use this architecturally as an accent light. And something I really like about this candela plot here is you can see the 0-degree orientation. So in this case, the 0-degree is going straight into and out of the wall here. Notice the weird little notch right here. That actually comes through right onto the wall. You can see the notch in the distribution right there projected onto the wall. And in fact, that notch is an artifact of the housing and the way that light reflects off that housing. So the outside wall, the wall inside the luminaire further away from the wall is actually bouncing some light back directly into the wall, even though that's not strictly speaking the intended distribution, which leads to the notch you see here and the notch you see on the wall. So these Candela plots are giving us a lot of information for exactly how that distribution is going to appear in the real world. Got two more examples. Okay, here's an interesting one. This is a fancy lamp, fancy enough that it was measured in a goniophotmeter. So here's that lamp's distribution. You've got kind of an interesting layout here that is due to an interaction with the lamp shade. And the question is the same. What is the symmetry of this luminaire and how are we utilizing it? So this luminaire is in fact actually symmetric, and almost always a table light lamp like this is going to be a task light, oftentimes a reading light that you're putting next to a chair. So the way we know that this is actually symmetric, other than the fact that this lamp is round, and so it seems fairly intuitive that you could just rotate this and not have a whole lot of change. The other way we know that this is actually symmetric is, again, it's not providing us a different distribution for 90 degrees horizontal. So that means both 90 and 0 are identical. So if we have no change at all as we rotate it, it's going to have to be actually symmetric, even if it's a weird, actually symmetric luminaire. And of course, the axis it's symmetric along is this one. And our last example, here's a weird one. So this is, let's call it a designer luminaire. And here we have the distribution of that luminaire. So same question as before. What is the symmetry of this luminaire and what are we using it for? This luminaire was a little more straightforward to judge. It's clearly asymmetric, and I can't imagine a use for this other than decorative. This is clearly a decorative direct view kind of luminaire, and based on that quagmire of a Candela plot, it's very asymmetric. Okay, so I hope this gave you some intuition as to what these Candela plots can tell you and how you can utilize them to understand your light sources. Do click that link you see, the DM Lights blog. That actually is where I got all of these Candela plots from. So you can go take a look at a couple more examples, and they do break that down nicely. So I do try to reference some useful sources throughout this lecture, and most of those links are going to be clickable. So you can take a look there. There's also photometry practice problems on the class page, so you can get some more practice utilizing that as well. But for now, this does bring me to the end of class today. I appreciate your time and attention and your effort that you put into figuring out solid angles, because these are not easy.